Alrighty, guys. So today we're starting on the second page. The first thing that they're going over is what G's means. Like, if somebody has 1 G of force, then they would be experiencing the acceleration of 9.8. If they have 2 G's of force, what would you do? It's just doubled, yeah. So if you have 3 G's of force, it's just tripled. But on Mars, we actually have less gravity. And so if we ever did travel to Mars, if we ever did have like a colony on Mars, the original Earthlings that end up there are going to be able to jump higher. There's less gravity, right? And then their muscles would atrophy to be normal, and then unless they worked out a whole lot, and then they wouldn't be able to make it here on Earth, because their bodies would get used to the gravity there. What? Yeah, so that's easy. If we already know the force on Earth's surface, if somebody weighs 980 newtons, they're 100 kilograms. But we just multiply that by a factor of 0.4. 0.40 G's, right? We just need to multiply those together. I think it's like 392, and then they said 2 sig figs or something like that. That's why it looks like this, the answer here. Okay, so if you're like, Mr. Guan, I got something different. Is it just a rounding thing? Double check that. All right, number 4. Find the weight of an 80 kilogram person on Earth's surface at an altitude of 2,000 kilometers. This one, they're out in low orbit of space. So we have what's here? The center of the Earth. See, center. We know that getting from here to the surface of the Earth is called a... From the center to the outside of a circle is called a radius. And then we're not at the radius. We are further than the radius by 2,000. I'm going to write that as 2.0 times 10 to the 6th meters. I'm converting already. What was the radius? Right. If you round that to 6.4 times 10 to the 6th, I converted already, right? So when I set up my equation, force of gravity equals G m1 m2 over r squared. G is equal to, do y'all have that memorized already?
6.67 times 10 to the negative 11.
All right. This is easy because my G's often look like 6's. This is easy because it's 6.67 times 10 to the negative 11. This is easy because it rhymes, 7 and 11. This is easy because your generation is a weird fascination with certain numbers that I will never understand. We've got 80 kilogram object, and do you have the Earth's mass memorized?
5.98 times 10 to the 24.
Good. 5.98 times 10 to the 24. M1, M2. What's the radius squared?
The radius. Wait, don't we also have to add the? Oh yeah,
Yep, I added them together. If you show your work and you write here inside these parentheses, show that you're adding those two numbers together, that's great. Not a big deal. As long as you make sure you have your parentheses correct, the calculator could do it for you. But I just summarized it like that. I think you get 455 because that's what it says the answer is right next to the problem. Try it. Plug it in the calculator, practice those problems. All right, the last one. A planet has half the mass of Earth and half the radius. How much would a 100 kilogram man weigh on this planet? All right. So if we say Fg equals G m1 m2 over r squared, my G is still 6.67 times 10 to the negative 11. My M1 is the 100 kilogram man, or Earth, doesn't matter. 100 kilogram man. But what are we going to do to Earth's mass? So I could put 5.98 times 10 to the 24 here. But then we're going to divide that by 2. What else? Half the radius. So if I put, 6.4 times 10 to the 6 here, I need to divide it by 2. And don't forget to square it. That's the long way of doing this. What's the easy way of doing this? What's the shorter way of doing this? So, yeah, if we cut the mass in half, we have the 100 kilogram man times the acceleration, right? F equals ma. That would be for Earth. If we cut the Earth's mass in half, what do we need to do? We need to divide by 2. I multiplied by 1/2 right there. So that's dividing by 2. And then if we cut the radius in half, that must mean this planet is way more dense. And we're closer into that denseness of it, so we get sucked in. So, right. And that's because that 2 at the bottom over here gets squared, right? This 2 down here, that 1/2 got squared. And so on the inverse squared, if you're half the distance, you're 4 times the amount of gravity. If you're twice the distance, you're 1/4 the amount of gravity. Okay. These are sample problems that we just didn't have time to do yesterday. We're done for today. We're going to talk about orbital motion tomorrow. Let's take a look at the calendar.